Okay, here we'll take a look at a sample problem using the phasor. So for this one, this is a really simple one because this is a AC source with a series with a resistor. So this is really easy. You don't necessarily need the phasor, but of course it really asks you, what is the phasor? So which is nothing but the amplitude of the sinusoidal. Okay, so yeah, let's see. So it says the resistance R is 200 ohm and the sinusoidal alternating EMF device operate at EM equals 36 volt, and then FD is the frequency. Okay, it's the frequency. So the angular frequency will be 2 pi FD. Okay, and then A, what is the potential difference VR across the resistance as a function of time t, and what is the phasor VR? Okay, so VR of t is nothing but, okay, so this is E, so this is actually EM cosine of d omega t. So actually it just connect to the resistor. So VR is nothing but this one. It's nothing but this one. So it is actually 36.0 cosine of 2 pi of FD. 2 pi FD. FD is actually 60.0 hertz, and then T. Okay, so this is it. Okay, and then if you can slightly simplify it, it is actually 36.0 cosine 120 pi T, and then SI unit is volt. Okay, so this is the question to the first half, and then it asks you what is the phasor. So the phasor is nothing but 36.0 volt. Okay. Okay, so it is really easy. So for part B, what are the current IR in the resistor and the phasor IR of T? Okay, so IR of T is nothing but VR of T over capital R. Or maybe you can use the phasor first. You can actually calculate the phasor first. IR will be VR over R. Okay, so this one is nothing but 36.0 cosine of 120 pi T over 200. So this is nothing but 0.180 cosine of 120 pi T, and then this is A. Okay, so this is IR of T. Okay, so this one will be 36.0 over 200, so which is nothing but 0.180A. So for the resistor, it is really easy. Okay, so next one, we consider a AC source connected with a capacitor. So it says capacitor C is 15 microfarad, and then blah blah blah. EM, FD are the same, and then what is the potential difference VC of T across the capacitor, and then what is the phasor capital VC? Okay. Okay, so actually VC, this is the phasor. Usually we use a capital letter to stand for the phasor. VC will be nothing but EM, so it is nothing but 36.0 volt. Okay, and then V or VC of T is still the same thing, was 36.0 cosine 120 pi T. Okay, it's actually the same as the previous one. Okay, so here part B. Okay, what is the current IC of T and also the phasor capital IC? Okay, of course you can just use I of T equals C dV of T dt. Okay, actually you can just use the differential equation. Okay, but if you don't want to use the differential equation, you can just use the phasor. And yeah, so okay, so this is just like I of C equals J omega C VC. Okay, this is actually 1 over ZZ. Okay, because you know VC equals IZ ZZ. Okay, ZZ equals 1 over J omega C. 1 over J omega C. Okay, so if you just move it over, IC equals J omega C VC. Okay, like this. Okay, so this is nothing but J, and then omega is 120 pi, and then C is this one, 15 times 10 to negative 6, and then VC is 36.0. So this number is J 0.203 A. Okay, so this is the phasor. This is the phasor. Okay, so yeah. So actually, after getting this one, we can directly write it as IC of T equals. So this one is actually an imaginary number. You can regard it as 0.203 exponential to J pi over 2. You change it to the polar coordinate, or the polar form of a complex number. Okay, so this is the amplitude, this is the phase, this is the phase. Okay, so the amplitude goes to here, 0.203, and then still cosine of 120 pi t. Okay, the frequency doesn't change, and then plus pi over 2. Okay, so the phase goes to here, the amplitude goes to here, and then this is A, like this. So we don't need to really play around with this differential equation. Of course, if you want to verify it, you can just plug in a V of t, VC of t equals this one, and then plug in there, and then finally you will get the same same answer. Okay. Yeah, cosine. Yeah. Okay. So the next, okay, we have a AC source connected with an inductor. Okay, so this is the inductor value, and then I'll ask you VL of t and also phasor VL. Okay, so this is actually the same thing. So VL is nothing but 36.0 volt, and then also VL of t equals 36.0 cosine of 120 pi t volts. Okay, so for part A, all the three are the same. Okay, so next, what is IL of t and also capital IL? Okay, so IL will be VL over ZL. ZL is nothing but J omega L. Okay, so this thing is nothing but a ZL. Okay, so we have a 36.0 over J omega is 120 pi, and then L is this one, 230 times 10 to the negative third power. Okay, so this is negative J 0.415 A. Okay, so this is a phasor. Okay, and if you change it to the polar form, it will become 0.415. Okay, this is the amplitude. This is the amplitude. Must be a non-negative number. And then it changed to exponential to negative J pi over 2. Okay, or you can write it as a J negative pi over 2. So this part is the phase. This is the phase. This is the amplitude. This is the amplitude. Okay, so finally IL of t should be 0.415 cosine 120 pi t minus pi over 2 a. Okay, put this one here and then put this one here. Of course, for these three examples, you can still use the differential equation to handle everything. But if so, actually, you can still use a v of t equals L di of t dt. Okay, you can just use this one. But actually, this one you need to do the integration, so it will be more complicated to find I. Okay. But generally, phasor will be useful in some more complicated case like this one, series RLC circuit. Okay, so here is a series RLC circuit. I would like to let you notice that this one is different from the previous one, like yeah. No, not this one. It's different from this one. This one is still RLC in series. The order doesn't import. Is not related. It is still RLC in series, but here we don't have any source. We don't have any source. Any kind of AC source, DC source. We just assume there are some energy stored in this circuit, so it will start to oscillate. So it will, as much as here we have a resistance, so the energy will be lost here. So you can see the amplitude will be attenuating. 那个振幅在衰减的，这个因为这个是 exponential 一个负的指数 ，so this one is attenuating 是衰减的。它t 大起来的话，这个就会变成零，就会慢慢衰减下来。Okay, so this one, for this one, we have an AC source here. We have an AC source here. Okay, so the point we need to learn phasor is that actually you can still write the ODE, to describe this circuit. Okay, so you can finally write like a second order ODE and then equals a sinusoidal. Okay, so it will somehow like the second derivative of I, and then plus something di dt, and then plus something I equals something cosine of omega dt. Okay, do something like this. Okay, so you know how to solve this second order ODE with the input. So you just let the right hand side to be 0, and then you try to find the complementary solution. Okay, to find the complementary solution, you need to write out the characteristic equation. Make the second derivative become s squared, this one become s, this one become 1, and then solve the second order algebraic equation. And then you find the roots to see whether it is distinct real roots, repeated real roots, or complex conjugate gate roots. Okay. And then after finding the complementary solution, you can just assume the particular solution is also cosine and sine with the same frequency, and then you plug in there to find the coefficient. Okay, so finally you will get the complete solution with something like the complete solution will be something like a exponential to s1t plus b exponential to s2t plus C cosine of omega dt plus D sine of omega dt, something like this, okay? But it takes you a lot of effort to solve the ODE or even to write out the correct differential equations. Okay, so it takes a lot of effort. So the point we need to learn phasor is that we don't need to play with the differential equation. Okay, we just need to change R to be the phasor, which is R itself, C to be 1 over J omega C, and then L becomes J omega L. And then it looks like this 1, 2, 3 in series. So the total impedance is the summation R plus 1 over J omega C plus J omega L. Okay, so this is the impedance. The impedance will become R plus 1 over J omega C plus 1 over J omega L. So it turns out to be J 1 over, omega L minus 1 over omega C. Okay, because this is 1 over J, so you multiply J, so J squared will be -1. So we have a negative sign here. So this is the impedance of this circuit. And then you just need to plug in the values. Okay, so you have EM, and then if you already know R, L, C, and also omega, and then this is just a complex number. This is just a complex number. Okay, and then finally you can quickly find I to be another complex number, and then the complex number you change it to polar form, and then it will convert back like this form. So you don't need to play around with that one. Okay, so one point is you only get sine of omega dt minus phi. Okay, and then you can actually change it to something like sine of omega dt, and then cosine of phi, and then minus cosine of omega dt sine of phi. Okay, in high school trigonometry, you know this sinusoidal with the addition argument, and then you can change it like this. So you only get this term and this term. You can't get the complementary solution. But the idea is usually we don't really care about this thing, because when t is large enough, and then s is has a negative real part, if s have a negative real part, it will tend to 0 after some time. So what we concern is the so-called steady state 稳态 steady state 稳态。稳态就是说这些 complementary solution 都衰减到0了，那我就不是特别关心，因为这个particular solution 会跟这个输入有关，我就只关心跟输入有关的部分这个就是它慢慢会稳定之后它就消失不见了 ，OK， 所以我就关心那个 steady state。Okay, so actually it directly tells you that the phasor of the current will be like this, EM over this thing. Okay, and of course Z is actually ZR plus ZL plus ZZ equals R plus J omega DL, right? Okay, actually this one I should be like EM over the absolute value of Z. This one is a complex number or a complex function if you consider omega D is a variable, it's a free variable. Okay, it's like a function or a complex function or complex number. Okay, so here we need to consider the absolute value. The absolute value, for example, if Z is, let's say Z is alpha plus J beta. Okay, the absolute value of C should be alpha square plus beta square, and then take the square root. Okay, so this thing is actually R square goes to here, and then this is the imaginary part. This part square goes to here, and then take the square root. Okay, so this is actually this thing. You may ask why you would like this. Actually, if you really, I'm not sure. Maybe I just slightly why about how to get those steps so that you can be more familiar with how to write the ODE. And also, here we have the phase. We also have the phase phi. We have the phase phi. So this phi will be like omega dl or minus this one. This is the imaginary part. The imaginary part of the C, and then this is the real part. So it is like yeah, this is Z equals alpha plus J beta. This is phi. This is phi. This is alpha. This is beta. So phi tangent phi will be beta over alpha. Okay, so this is the imaginary part, this is the real part, like this. I don't write phi to be arctangent of this one because arctangent only goes to negative 90 to 90. It cannot really go to the second and third quadrant. Okay, so for the principal value, so yeah, I just let it like tangent phi to be this value, and then you need to determine which quadrant it is in to see this phi should be in first or fourth quadrant or second or third quadrant. And here, as I mentioned, this omega d wouldn't change. For the previous case, if we don't have a source, then the natural frequency will be slightly smaller than this 1 over square root of LC. But here, as I mentioned, this is a linear system. If we have a sinusoidal input, the output should have the same frequency. So here, the omega d doesn't change at all. And what does it mean? This is so-called the resonant frequency, 共振频率, which means that if we have the imaginary part to be 0, which means that the imaginary part of Z to be 0, then it will be resonant. There is no energy, no total energy stored in here. It turns out to be a real impedance. Okay, so if the imaginary part of a C equals 0, it will just like omega dl omega dl equals 1 over omega dc. Okay, so you move this up, move this down. Okay, omega d will be 1 over square root of LC. Omega d will be 1 over square root of LC. So this is the resonant frequency. Okay, so I just slightly let you know how to write out the, so just tell you why this is correct. Why this is correct. If you don't trust, you can just try to practice it. But the mathematics is very, very tedious. But just slightly let you know. Oh, so this is EM equals EM cosine of omega dt, and then this is R, and then let's say this is VR, this is VC, this is VL. Okay, so pay attention to the polarity. This is plus minus, plus minus, plus minus. Okay, like this. So in that case, we will have EM cosine of omega dt equals VR plus VC plus VL. Okay, equals R times I. Okay, if this is I. Okay, and then plus VC plus VL. VL will be L di dt. Okay, and also we will have I equals C dVc dVc dt. Okay, so we can just plug in this one to here and also here. So we will get RC dVc dt and then plus Vc plus LC and then the second derivative of Vc dt 2. Okay, so the right side is actually the same as the damped oscillation, but here we have the sinusoidal source. So in that case, it will look something like the second derivative of Vc dt2 plus R over L. You just divide both sides by 1 over LC. Okay, so it becomes R over L, and then here it becomes 1, and then dVc dt, and then plus 1 over LC, and then Vc equals Em cosine of omega dt. Okay, so the idea is we need to solve for the complementary solution S squared plus R over L S plus 1 over LC. Okay, so we will have the complementary solution, but actually we don't really care about it. We just assume it does not have the same frequency as this one because this one should be a positive value. Okay, it can't be a pure imaginary number, so it can never be a pure cosine. So yeah, we just assume this complementary solution will tend to 0 when t is large. Okay, so then we just ignore it. Then finally, we can just assume our Vc will be A cosine of omega dt and then plus B sine of omega dt. And then you plug in this one to there, and then to try to solve A and B. And then finally, you get AB. The square of them, okay, if you pick a squared plus b squared and then take the square root, this will be actually the same as this term. Okay, actually the same as this term. Or if you just extract it back to there, you will find this is a sine of omega dt, a cosine of omega dt, and then with the coefficient, this will be negative a, this will be b. Okay, so you just need to pay some effort to calculate all those things, because you need to plug in this one to a secondary ODE, and then you will need to compare the coefficient. Okay, so I don't try to repeat the complete things, because yeah, you can try to practice it at home. Okay, so maybe let's have a 10 minutes break and then we will go on.